Hello again. This is another video on chapter 7. We are going to solve trig equations in this video. I hope you're doing well. So let us get started. Let's start with solving. I already did solve two simple equations before, but I'm going to repeat them here. That's okay. So one was a situation where we had a simple equation cosine x equals to 1/2. Now to solve a trig equation, we isolate x. Obviously we're looking for values of x, so we have to isolate x. So to isolate x, we have to use cosine inverse. So we take cosine inverse of both sides, and this is what we end up with. Cosine inverse of cosine x equals to cosine inverse of 1/2. And now cosine inverse of cosine x is just x. And now what about cosine inverse of 1/2? Well, when you put this in the calculator is going to look in this area here for an angle whose cosine is 1/2. And we know this is 1/2 on the x-axis, on the cosine axis, right? So we know this is the angle. And we also know in one complete turn, here is another angle right here, right? But we don't know the values of them. Of course, you should memorize these, as I said. But suppose you don't have them memorized and use a calculator. Well, calculator gives you this one, 60 degrees, because calculator only looks over here for cosine, for angle that has cosine 1/2. So it finds this for you. But that's good, because using that, we can find the other one too. So from 0 to 2 pi, right, there are two angles that have cosine 1/2. One of them is this one, 60 degrees, which in radian is pi over 3. So one of them is pi over 3. And the other one is this angle here, which obviously, if you take 2 pi and take away pi over 3 from it, 2 pi is 6 pi over 3 minus 1 pi over 3, because this is pi over 3 as well, right? Because this is symmetric here. So that's 5 pi over 3, right? So there is pi over 3 and 5 pi over 3 that have cosine 1/2. But this is not the only angle. We could go around and come to this. That means we can add 2 pi to it and get another angle that has cosine 1/2. And we could keep doing that. We go around twice. Once, twice, and come over here. So there are infinite number of angles that have cosine 1/2, and they're all come from this equation here. Now, what about the other angle, this one? We can't get this if you add 2 pi to that, right? So we have to consider that as a separate equation, and we do that here. So either x is pi over 3 plus 2 pi k, or x is 5 pi over 3 plus 2 pi k, and k is an integer. So these are all the solutions for that equation. Okay? All right, so let's look at another example. In this case, the argument of cosine is not x, but is 2x. Well, we solve it the same way. We take inverse, cosine inverse of both sides. There you go. Cosine inverse of this side, left side, equals to cosine inverse of the right side. So that gives us 2x, not x, but 2x, right? So 2x comes out here. So we're going to look for angles whose cosine is negative square root of 3 over 2. Now, negative square root of 3 over 2 is about right this much, right? So what angles have this cosine? Well, this one and this one, right here, right? And this one. So those are the two. Well, now what do you get if you put in a calculator? Calculator is going to look over here from 0 to pi for an angle whose cosine is negative square root of 3 over 2 and gives you 150 degrees. If you put the calculator in degree mode, it's more intuitive where the angles are, okay? So 150 degrees in radian is 5 pi over 6, because pi over 6 is 30 degrees. Okay, so that one is 5 pi over 6. And what is this one? Well, remember the reference angle is pi over 6. So this one would be 7 pi over 6, right? This one is 7 pi over 6. And those are the two in one complete turn. And that's it. All right, now, these are not the solutions to this equation. These are the angles that make the right side, right, cosine inverse negative square root of 3 over 2. But we're not looking for solutions for 2x. We're looking for solutions for x. So 2x equals to that gives us, so this equation gives us solutions for 2x, but we don't want that. We want to divide both sides by 2. So divide by this side by 2 and divide these by 2, divide this by 2, divide this by 2. What do we get? Well, we get x equals to 5 pi over 12 plus k pi, not 2 pi, because we have to divide both of these by 2. And k is an integer. We do the same thing for 7 pi over 6. We get 7 pi over 12 plus k pi. Okay, now we have all the solutions for this equation. All the solutions for this equation, right? We use the unit circle to find the angles that work on the right-hand side. So this way we were able to write these two equations. All right. Now, if you think about this equation, you can think of it as y equals to cosine 2x and y equals to negative square root of 3 over 2 as two separate functions. Now, if you graph y equals to cosine 2x, you get this right here. See? We get this graph. And if you graph y equals to negative square root of 3 over 2, we get this horizontal line here. You can think of the solutions for this equation as intersection points of the graph of cosine 2x and the graph of negative square root of 3 over 2. So we're looking at this from a different angle, from a geometric kind of angle to this equation. So this is equivalent to figuring out the intersection points of these two graphs, the green one and the red one. So if you want to find some specific solutions, well, we have to let k be different numbers, and for every k we find a solution. Now if you let k be 0, from this equation we get 5 pi over 12, which is over here. 5 pi over 12 is 75 degrees. That's one solution. Solution is the value of x, which is 75 degrees, or 5 pi over 12. And then the other equation, 7 pi over 12, if k is 0, gives us 7 pi over 12, which is this one. 7 times pi over 12 is 15 degrees. So 7 times 15 is 105. So that's another solution. When k equals to 0, we get two solutions. Now when k equals to 1, we get two more solutions. One from that, from the first one, and one from the second one. So when k equals to 1, we get 5 pi over 12 plus 1 pi, which is 17 pi over 12, which is 225 degrees. And from the other equation, we get 19 pi over 12, which is 285 degrees. So this is 4 solutions in one complete turn. And of course, you know the period of this function on the left is pi. So wave number is 2. That means in one complete turn, 2 pi, we have 2 cycles of cosine. You see 1 and 2 up to here. You see this is 2 pi. In 2 pi, there are 4 solutions for that equation, right? So think about it. If this was 10 pi here, 10x, then you would have 10 cycles in 2 pi. And for every cycle, we will find 2 solutions. So that would be 20 solutions, right? If this was cosine 10x. All right, so that's the idea. It's a different angle of looking at a trig equation. Of course, you can do that for any equation in algebra. In 2D, you can think of what? Intersections of 2 graphs. Now, you may not have solutions, right? So if you put like x squared equals to -4, you're not going to find any real number solutions. These two don't intersect because x squared is over here and -4 is over here. They don't intersect, so there are no solutions. All right, so here they do intersect at infinite number of intersection points. Here's another equation. This is cosecant. Now, whenever we have cosecant and secant, we don't work with them directly. We can work with the reciprocals. All you have to do is take reciprocal of both sides. Now, reciprocal of cosecant is actually, cosecant is 1 over sine equals to square root of 2. But if you want to, easier way to do it, instead of writing cosecant as 1 over sine, why don't we just write cosecant and as sine and then take reciprocal of the right hand side, right? So these two equations are equivalent because by writing cosecant as sine, you're actually doing 1 over cosecant, right? And then we do the same thing to the right hand side. So it's much easier than writing it this way, right? So whenever we have cosecant equals to a number, then we make it sine and then take reciprocal of that number. Now, instead of solving this equation, we just solve this equation, right? And now what is the answer? Well, we are going to take what? We're going to take sine inverse of both sides here. And we end up with 1/3 x minus pi equals to, now, what is sine inverse of 1 over square root of 2? Well, 1 over square root of 2 is some number. So we're looking for the calculator is going to look for what? For an angle in a restricted domain of sine, which is over here, that has that sign. And that angle that the calculator is going to give you is this one right here, which is, of course, pi over 4, right? So that would be pi over 4. So what do we write? We write 1/3 x minus pi equals to pi over 4, but that's not the only one, right? In one complete turn, there are actually two angles that have that sign. One of them is pi over 4. The other one is over here. And since we know this is 45 here, then this is 45. So that would be 180 minus 45, or pi minus pi over 4, which obviously is going to be 3 pi over 4, right? So so we got, so there are two solutions. One of them we get from two equations. to find the solutions. One of them is this right here with the pi over 4. So we use pi over 4 and we write this equation that 1/3 x minus pi equals to pi over 4 plus 2k pi. Because we can get here by going around many, many times, right, in different directions. That's one equation. And we write another one with 3 pi over 4. So we say 1/3 x minus pi is 3 pi over 4 plus 2k pi. But we are not done, because we were not looking for solutions for 1/3 x minus pi, but we were looking for solutions for x. So what do we have to do? We have to modify both sides of this two equations, right? So that we have x on one side by itself. And we do that. And you see it here. So if you add pi to both sides, pi plus pi over 4 is 5 pi over 4, because pi is 4 pi over 4 plus 1 pi over 4 is 5 pi over 4 plus 2k pi. So that is 1/3 x. And then the same here, we add pi to both sides. So 1/3 x is going to be pi plus 3 pi over 4. So 4 pi over 4 plus 3 pi over 4 is 7 pi over 4 plus 2k pi. Now we are not done, because we didn't want 1/3 x, we wanted x. So we multiply both sides by 3. Right? So here we get x equals to 3 times that plus 3 times that. And over here, x equals to 3 times that plus 3 times that. So we got two equations, this one and this one. And these two equations give us all the solutions for that equation, right? All the equation, all the solutions for that equation, right? Now, of course, this is cosecant, and we know cosecant has restrictions, right? So this angle right here cannot be an angle that is not in the domain of cosecant, right? So we have to take that into account. But all the solutions of sine equal to 1 over square root of 2 are given by what? By these two equations. All right, let me show you again here. What do we get? Well, let's see. If k equal to 0, then we can put 0 here and 0 here. We get two solutions. If k equals to 1, or k equals to 2, or k equals to -1, and so forth, right? So now, if you again think of solutions of this equation as the intersection of cosecant and square root of 2 as two separate functions. Cosecant is this green one, right? And this solution, y equals to square root of x, is this horizontal red line here. And the solutions for these equations are the intersections of what? Of the cosecant and what? And the square root of 2, as you see. Those are the solutions, right? We pick those as the solutions of the equations that we were given. Okay, so for example, if k equals to 0, we get 21 pi over 4, and which is, we get 15 pi over 4, which is 675 degrees, and we get 21 pi over 4 from the second equation, which is 945 degrees. So these are the two solutions we get if k equals to 0. Now, if you go back, right, if you get negative, if k equals to -1, right, if k equals to -1, then we end up with what? if it's k equals to negative 1, that would be negative 6 pi. And negative 6 pi with the denominator of 4 would be negative 24 over 4. I mean, you have to multiply it by 4. So 24 over 4. So it would be negative 24 pi over 4 plus that, it would be negative 3 pi over 4. And that would be this solution here. And then again, you put it in the other equation, you get another one, right? So we get, actually that one is this one. So if I put k equal to negative 1 on this equation, I get this one. If I put it in this equation, I get that one. All right, so you can put k equal to any integer, and you can find many, many solutions to the same equation. All right, here's another one. Just solve 2 cosine theta minus 3 equals to negative 5. And in this case, we are given a range of theta that we are only interested for solutions in this range, from 0 to 2 pi, not including 2 pi. Okay, well, we can find all solutions and then pick the k that gives us the solutions that stay in this interval. So we are going to isolate cosine again. We get cosine is negative 1. Then we take inverse cosine of both sides. So theta is inverse cosine of negative 1. Now obviously calculator is going to give you in this area what is an angle whose cosine is negative 1. There is only one angle, right? And in fact, in whole period of cosine, there is only one angle that has cosine negative 1, and that is pi. So we write it down. We say, okay, theta can only be pi plus 2k pi, because I can come here going around one time and then come here, right? Or many times. In fact, I could go the other way too. So theta is pi plus 2k pi. And now we don't want all of them. We only want the ones that are in this interval. And if you think about it, if k equals to 0, we get pi. So we get this one. If k equals to 1, then it would be pi plus 2 pi, which is 3 pi, and we go outside of this range. So we don't want that one. We stop. And if you put negative, of course, you get negative answers, which is outside of this range. So in this given range, there is only one solution for this equation. All right, here is another one. 2 sine squared minus 1 equals to 0. And we are interested again in solutions only in this range of values. Well, again, we isolate sine squared. Well, that's not good enough because we have to isolate sine. So what do? We take square root of both sides. So we get sine equals to plus and minus 1 over square root of 2. So that means we have two equations. We have to solve this one, find all the solutions for that one. We have to solve this one and find all the solutions for this one, and then decide on k that gives us what? Solutions only in this region. Okay, well, to solve the first one, we just put theta is sine inverse of 1 over square root of 2. And we know the calculator is going to give us this one. And that is pi over 4. So for the first equation, which is that one here, we have pi over 4. And we know there is another one that has that sign. And that is this one right here. And we know that is 3 pi over 4. All right, so we got our two equations for that. One of them is going to be pi over 4 plus 2k pi, or 2 pi k. And the other one is 3 pi over 4 plus 2k pi, right? That's only for that. Now, what about for negative 1 square root of 3? 1 over square root of 2. Well, if you use a calculator, calculator gives you see, this angle. Because calculator is going to look for an angle from negative pi over 2 to pi over 2. So calculator gives you this. Now, by convention, we like to write all the solutions in 1, 0 to 2 pi. We don't want to go to negative numbers. So what do? We say, okay, calculator gives us negative 45. But what is the smallest positive angle that has the same, negative sign, right? So we want this angle here. Well, the smallest positive angle would be this one, right? That has the same sign. So instead of using that, we're going to use this angle. So for this second equation, we write x equals to, now what is that angle? Well, remember, this is pi over 4. This is negative pi over 4. And if it's symmetric here, this also would be pi over 4. So that's pi plus pi over 4. So pi is what? Pi is 4 pi over 4 plus 1 pi over 4 is 5 pi over 4. So for this equation, we write y equals to 5, x equals to 5 pi over 4 plus 2k pi. And then, what about this angle itself, which calculator says is negative 45, of course is correct, but we are interested in a positive angle that has the same terminal side. That positive angle is 2 pi minus pi over 4, because we know this is pi over 4 here. Pi is 8 pi over 4, minus pi over 4 is 7 pi over 4. So this positive angle here is 7 pi over 4. So we write 7 pi over 4 plus 2k pi. So how many equations we have for this equation? How many equations do we have to use to find all the solutions for that? 4. 4 equations. So let me write all of them down in the next slide and work with them. Okay. All right. So we have 4 equations that can give us solutions, right? And those are this one right here, this one right here, this one, and this one, right? Remember, we got these from that equation, and we get these from the other one, right? Because this equation turned into 2 equations that we had to solve. Okay, so now remember, we're looking for answers only from 0 to 2 pi, and you can get those by letting k equal to 0 here, 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 and here. So in this first one, we get pi over 4 if k is 0. Over here, we get 3 pi over 4. Over here, we get 5 pi over 4. Over here, we get 7 pi over 4, right? Now, if k equals to 1, obviously all of these go out of the range because all of them have 2 pi, right? So we can't put k equal to 1. And if you put k equal to negative 1, all of them become a negative angle, and that's not going to work, right? So, for only k equal to 0, we have 4 solutions, and they're right here. And if we want to write them, usually we write them in a set like this, pi over 4, comma, 3 pi over 4, comma, 5 pi over 4, comma, 7 pi over 4. And we close the set, we say, this is a solution set in this interval for that equation. Okay, so you can stop the video and do this one more time yourself. Make sure it makes sense to you. All right, here's another equation, and this time we have tangent, and we are given a range to find the solutions. Okay, well, we isolate tangent here. How? It's like algebra. You don't want to isolate this term. It appears in both sides, but that's okay. We can put all the tangents in one side and isolate it, right? See? So we get 2 tangent here plus 6, and then you bring the tangent on this side, take the 3 to the other side, and so what do you get? So not 3 but 6, because you have to multiply by 2. So 2 tangent x minus tangent x equals to 5 minus 6. So we end up with this. So we solve this. We take tangent inverse of both sides. So we get x equals the tangent inverse of -1. Now again, tangent restriction is from negative pi over 2 to pi over 2, remember? So when you put this in the calculator is going to look where? Here, for an angle whose tangent is -1. And it's going to find this for you, which is negative pi over 4. Now, to solve equations that involve, tangent, one period of tangent is from 0 to pi. So if we look from 0 to pi and see how many angles satisfy that equation, and then we write an equation for each angle that we find. In this case, there is only one, and it's this one, right? Because remember, by convention, we look in a positive period from 0 to pi for tangent and cotangent, and for secant, cosecant, sine and cosine, we go from 0 to 2 pi. Okay, so from 0 to pi, there is only one angle, which is, what is that angle? Well, if this is negative pi over 4, this is pi over 4 here. So what is this angle right here? Well, that would be 3 pi over 4, right? So the angle that we're going to use in our equation is actually 3 pi over 4, is this one. Plus what? Plus k times the period, but we know the period of tangent is pi. So this is the equation that we get for all solutions for what? For that equation. All right, so what are the solutions in 0 to 2 pi? Well, we start by substituting 0 for k, we get that. If you put 1 for k, we get 3 pi over 4 plus 1 times pi, which is 7 pi over 4, and 7 pi over 4 is still in this region. It's less than 2 pi. So this is good, and this is good. That's 2 solutions. When k equals to 2, we get 11 pi over 4, which is bigger than 2 pi. Because 8 pi over 4 is 2 pi, that's 11 pi over 4, so we don't use it. It is a solution, but we don't use it because we are told to find solutions only in this region, in this interval. All right, and that's how we solve the equation that involves tangent. I think I did this one already for you, but I'm gonna let you look at it. I did it in the previous video. Sine x equals to 0.8. We take sine inverse of both sides, right? And we write 2 equations. The difference between this one and the ones I just did is because this one doesn't have a nice number that you can get one of those familiar, degrees, angles in degrees, like 60, 45, 30. It's just a decimal. So the answer would be just a decimal in degrees or in radians, right? So calculator is going to give you this one, which is 53.1, and you find this one by subtracting 180 minus what? Minus that much, and you end up with 126.9. Then you add 360 pi instead of 2 pi because we are working with degrees, right? So these are the 2 equations that give us all the solutions for that equation. And if you want solutions in certain interval, then you decide which one. You pick the ones that you want. But this is all solutions. All right? And if you do this in radian, and I think I did that already. This is in radian, right? The only difference is that the calculator now, if you put it in radian mode, the calculator doesn't give you 53 point something, it gives you 0.92, which is in radian. And to find the other one in radian, you have to take pi and subtract 0.92 from it. Now pi is like 3.14 minus 0.92 gives you 2.21. And then you add 2k pi to both, right? So the solutions for that equation are given by these two equations. All of them, right, in radian. Now here's another one. In this case, we have two different functions. We have sine and cosine involved. So we have to do some trigonometric acrobatics to be able to work with only one function, not two different ones. Now to do that, we try to make this look like this or make this look like that. Which one is easier? It is easier to make that one look like this because we can write it as 1 minus cosine squared. So we do that. So instead of sine squared, we write 1 minus cosine squared. And then we move everything to one side. So we're going to make it look like what? Look like a quadratic. We talked about that before, but you see it looks like that. If we let cosine theta be x, it looks like we are dealing with a quadratic function. Now, how do we solve that? Well, we could do it by factoring. We know this is just x plus 1 squared, right? But if you write it as x plus 1 times x plus 1, then x has to be negative 1. Well, this is equivalent to that if x is cosine. So if x is negative 1, then cosine has to be negative 1. So you see, that equation right here reduces to only what? That. So what do? We solve it. Solutions are equivalent. Solutions for this is the same as solutions for that one. So what are the solutions? All the solutions for this equation, well, we just take cosine inverse of both sides. So theta is, well, in one period of cosine, where is it that cosine is negative 1? Over here, pi. That's the only place. So we are going to write theta is pi plus 2k pi. Now, this gives all the solutions, but we want solutions only from 0 to 2 pi. So we let k be 0. We get theta is pi, so that's one solution. K equals to 1. Pi plus 2 pi is 3 pi, but that goes outside, so we don't want that. So there is only one solution. And if you think of this as, again, sine squared is one function and 2 cosine theta is another. If you graph them, that red graph is sine squared, and this green one is 2 cosine, or the other way around. The green one is sine. This is 2 cosine theta plus 2. So it has moved up to 2. So the red one is the cosine, and the other one is sine squared, right? So, so where do they intersect? Well, in 2 pi, these two intersect only at one point, right? Of course, they intersect again at 3 pi, which is 2 pi later, right? And then they intersect again over here, and then intersect again over here. But we are only looking at one of them, right? Remember, the green one is sine squared. I don't have it here. I should have, but so this is sine squared theta, or you can put x, doesn't matter. And the other one is cosine, 2 cosine theta plus 2. All right, so here's another one. Again, we are dealing with different functions. So now we have to do a little bit more acrobatics. Well, we have all the identities. Why don't we use them, right? If you try to isolate a function here, you'll be working a whole lot for no reason. You can go different paths and maybe harder paths and get a function on one side with a lot of work. But we want to find the easiest one, easiest way. You know, you want to go to downtown Houston, you can go to Galveston and come back and go, you know, to Beaumont and then come back, go to downtown. You reach downtown, but then that's a lot of driving for no reason. All right, so what do we compare this to? Well, you know, remember cosine alpha minus beta? If you look at your identity sheet, you can find one that matches this. Cosine, cosine, sine, sine, and they're added. You see, cosine, cosine, sine, sine, and they're added. So you can replace this with something else that is easier to work with. What? Well, think of alpha as x and beta as 2x. If you do that, then this whole thing becomes just cosine x minus 2x, and the right-hand side is just square root of 3 over 2. So we solve this equation instead of that, right? Okay, how do we solve it? We take cosine. First of all, we can simplify it because x minus 2x is negative x. And we know cosine negative x is the same as cosine x. So this is just cosine x equals to square root of 3 over 2. This whole equation is just that. We solve this instead, right? This might come from some application problem. And you see how identities help us solve this equation easily. So what do? We find cosine inverse of cosine, which is x, and cosine inverse of square root of 3 over 2. So in one complete turn, what are the angles that have cosine square root of 3 over 2? About right here somewhere. Is that one? And what? And this one, right? Now, what is that angle? Well, you can memorize it, you can use a calculator, but we know it's pi over 6, right? Which is 30 degrees. So one angle is pi over 6. So we write pi over 6 plus 2k pi. Which one is that? What is that? Well, that would be 2 pi minus what? Minus pi over 6, which is 11 pi over 6. And so 11 pi over 6 plus 2k pi. All right, now we didn't want all the solutions. We just wanted the ones that are in this interval. Well, if k equal to 0, we get pi over 6 and 11 pi over 6. And if you let k be any other number, you go outside of this region, and it's not going to work. So there are only two solutions for that equation. Okay? All right, here's another one. Well, again, we take tangent inverse of both sides. So we're looking for x, right, minus pi over 2 equals to tangent inverse of 1. So we put tangent inverse of 1, calculator is going to look for what? It's going to look for an angle here that has tangent 1. And we know that's pi over 4. So it's going to give us pi over 4. And that is the only angle in one period of tangent that has that tangent 1. So we write pi over 4 plus k pi, okay? But we are not done because we didn't want solutions for this. We want solutions for x. So what do? We isolate x. So x is pi over 4 plus pi over 2. If you bring it over here and add pi over 2 here, pi over 2 is 2 pi over 4 plus 1 pi over 4 is 3 pi over 4 plus k pi. So now to find the solutions in this interval, we let k be 0, we get that, k1, we get that. So there are two solutions. This 7 pi over 4 is still less than 2 pi. because 2 pi is 8 pi over 4, right? All right, so that's it. All right, so I'm going to now talk about axes that contain the values of the 6 ratios, okay? This is not directly in the textbook, not all of it. So, but it's very useful in trigonometry. So I'm going to quickly go over it and tell you about it. You can stop the video and think about it if you want. But if I go to, let me click on this. My audio might be a little bit messed up. All right, because it puts a lot of load on the CPU. All right, notice that when I change this, you see, is graphing the tangent. See that? Is graphing 2 cycles, several cycles of tangent, and I go to from negative 360 to 360, right? That blue graph is actually tangent. I can go 1 degree at a time, and you see it. See that is graphing, you see. There you go. There you go. So now think about it. At this point right here, tangent, if you extend the, we're over there, so let me move it in the first quadrant first. I'm not in the first quadrant. Let me go back to the first quadrant, maybe over here. So you see that distance from here to here, if you tangent a number line to this point, 1, 0, this is like a number line, then this value, this distance from here to here is actually the tangent of this angle. Why? Because, well, it's opposite, which is this distance, over 1, which is the unit circle, right? So it would be that distance. So let me go back to, let me close this and go back to our, all right. So as you see, this distance right here, this distance is tangent, because the tangent of this angle is opposite over 1. And in this case, tangent of pi over 4, of course, is pi over 4 is 1. And you know, this is the radius is the same as 1. So what's tangent of this angle? Well, it's from here to what? To here. So this is positive infinity and this is negative infinity on this number line. And the tangent values are given by those distances. Now, if an angle is on this side, and if you extend the terminal side, you don't hit tangent axis, that's what this is, then you can extend it backwards and hit it. And this distance here now is tangent, but since you're going on this side, is negative 1. So tangent of this angle is actually negative 1. It's the same as tangent of this angle. If you come all the way around here, like if your terminal side is here, then you extend the terminal side, you hit this, the angle is still the same, negative 1, the tangent. Okay, so that's a good thing to know, that if this is, if from here to here is cosine and from here to here is sine, then this axis right here is tangent axis. Okay? So this distance right here is tangent, or this distance. And I explain it here. You can stop the video and read this carefully and see if that makes sense. And if you go to the notes, you can click here and play with this GeoGebra animation. Okay, what about cotangent? Well, cotangent also is going to be over here. A number line that is tangent to 0, 1. These are positive angles, and these are negative numbers. So what's the cotangent of pi over 4? Well, you extend it until you hit this, and obviously this distance is the same as this distance here, right? So so that distance in this case, of course, is 1, right? Because it's the same as radius. So what's cotangent? Cotangent is the distance from here to here, right? And that is, it should be a positive 1. Okay, cotangent of 7 pi over 4 is negative 1. That's positive, that's the typo. So cotangent of pi over 4 is 1, and cotangent of 7 pi over 4 is negative 1. Okay, as right here, this is 7 pi over 4. Again, if I extend it this way, I don't hit the axis. So I go that way, hit this. This distance from here to here is cotangent. So this way you can actually figure out tangent and cotangent of any value. Let me make this plus, keep it there. So, you know, what is the cotangent of this? Well, this way I don't get anywhere, so I go backwards. So cotangent would be from here to here. And it's positive because this is positive. This way is negative. All right, and again, if you click on this in the notes, you see an animation that you see as this goes around, the cotangent is graphed. All right, so remember this was a plus 1. All right, so what about secant and cosecant? Well, I remember when we were in high school, we took trigonometry, and the teacher the 4 axes I just talked about, cosine, sine, cotangent, and tangent, and he said, you go home and here's your homework. Figure out where the axes for secant and cosecant are. And of course, we spent the whole night until 3 o'clock in the morning trying to figure it out. So, and we did. So I still remember. So what is the cotangent, what is the secant and cosecant axis? Well, if you think of the, let's see, this is secant. So let me see which one I gave you first. Terminals, okay, for example, so this is cosecant. So to find cosecant, you can think of cotangent axis. Let's say I want a cosecant of this angle, right? So I'm going to extend it until I hit cotangent axis. Then the distance from here to there is cosecant. And now you see, you can think of cosecant axis and secant axis, and a number line that goes through the terminal site. So this axis that actually turns with the angle itself is both cosecant and secant axis. The distance from here from here to the point of intersection of cotangent and this axis is cosecant. And if you put tangent here, tangent axis here, then the distance from here to the point that it intersects the tangent axis is secant of that angle. And again, I'm not going to test you on this directly. So this is something for you to stop the video and see if it makes sense to you. I explain it here, and just imagine different angles like I did here and see if it makes sense, okay? So cosecant of pi over 4 from here to there, that distance right there is square root of 2, okay? Which is basically 1 over sine of pi over 4, so it's 1 over, so it's 2 over square root of 2, and if you rationalize it, you get what? You get square root of, right? Now, what about an angle that is over here? Well, an angle is over here, then you don't get anywhere if you do it. You go this way. So you go the other way, backwards. You hit the cotangent. Then the distance from here still is cosecant, but is negative. Why? Because you go backwards. So if you extend the terminal side backwards and find the distance, that's negative. All right, and the same thing is true for secant. So you put the tangent axis here, and then you extend the terminal side of the angle until you hit it. Distance from here to here is the secant of that angle. In this case, of course, is square root of 2 again. And if you're somewhere else, let's say if you're over here, then this way doesn't get you anywhere, so you go backwards. You hit the tangent, and you find the distance from here to here. That's negative the square root of 2, because you go backwards. Okay? All right, now let me put all of them together, and I'm going to show you this animation. And for this animation, let me click on this. Again, my audio might be a little bit messed up. I want to wait for it to load. All right, I'm just going to animate it. And notice that as the angle is going around here, as you see it right there, these different vectors are actually the absolute values of the 6 trig functions. Okay, let me move it down so I can stop it maybe right here. But oops, go up. I'll make it smaller maybe, so I move it over here, make it bigger so you can see it, and let me run the animation. So you see there are 6 vectors here. Let me make it go around so I can stop it in the right time. Right there somewhere. So at this point right here, well, we went too far. Make it go around. All right, so you can play with this and you see it. See right there, 6 different ratios are given with those vectors actually. 6 different ratios are given with those vectors. I'm going to stop it when it comes down. Then here, you see? So this is the angle. So this right here is secant. This right there, and you can barely see that arrow, that's cosecant. This right here is sine, right? I mean, the angle is over there. So this point on this unit circle right here gives you the angle. So you have to go backwards to find the secant. So that's secant, that blue one. And then this is the sine, right? This is the cosine. And from here to here is cotangent. I mean cosecant. And from here to here is cotangent. So there's 6 vectors here, and the vectors give you the 6 ratios. All right, so I wanted to make sure you see this. This was in 1960s textbooks. They had this, but after 1960s, somehow this idea disappeared in trig textbooks. In fact, there are some teachers had these for students to play with. These are mechanical kind of a device with, cardboard that you can actually move this thing around and see different values of the 6 ratios. But I don't do that anymore. I'm not sure why, but I did it for you. So I'm going to stop the video here and talk about modeling with trigonometric equations in the next video. Okay, so I'm going to come back here and say bye to you, Take care of yourself and others, okay?